Good morning, sir.
Yes, after probably 1.5 weeks. Huh?
Yes, sir.
Okay, I had got one operation. For that, I was away. Anyway, to a real situation. Up till now, we had discussed what is single reinforced section, what is double reinforced section, what is single, why double reinforced, and we had studied and that the beam is not only subjected to bending moment, it is also subjected to shear force, and how to safeguard these things we had studied independently. We tried to find out if in single reinforced section, we tried to find out if the cross section and amount of steel is given. We will try to find out the moment of resistance. Then if moment of resistance is given, section is given, we try to find out the amount of steel required. Similarly, for double reinforcement, if moment of if factored moment is given, cross section is given, then we try to find out moment area of steel with respect to tension and with respect to compression. Okay, and independently, if a member is subjected to shear force, we try to find out whether shear reinforcement is required or not. If shear reinforcement is required, we have to provide the reinforcement. We had studied here the regard stirrups. We had not studied the bent of bars because in our normal construction, the bars are not bent up, rather it is curtailed. But in exceptional construction, say in case of the bridge, the bars from the bottom zone is transferred to the upper zone, but here it is not done. Now, all these things we have to assemble together, which is the real structure. So that's why it is a design of beam. Now here you will see, but already you are looking because it is visible for you. We have to obey the IS 456, right? Now, when we are to design, what informations will be in our hand? In our hand, information will be available only the span, the length from support to support. If it is a simply supported condition. If it is a fixed, this continuous beam, we will study continuous beam later. If it is a continuous beam, it will give center to center distance of the different columns. So now let us see only which is simply supported beam. So there are some specification in code. We are having span, and will be given the utility for what the beam or the structure is going to be utilized. These two information will come to our hand. Now we have to find out the cross section required, the grade of concrete. We have to find out the amount of steel required, since our this chapter is single design of single reinforced section. So we have to find out the tension steel that is going to provide at the bottom for simply supported beam. So these things you have to find out. We have to fix the cross section of the member. So how to fix the cross section of the member? How to fix the cross section of the member? So for that, IS 456 gives some guidelines. Say basic rules. Effective span. Span is given. A common man is given that the beam of my structure is such and such. Now we have to find out the effective span. And when we are talking about the effective span, so this given in clause, the effective span can be simply supported, can be simply supported beam or slab can be again. Now, the beam will rest on support. The beam will rest on support. That support may be column. That support may be wall. That support may be wall. So the the two words now come: clear span, total span, effective span. If it is single span beam, then total span is distance between outer to outer face of the column. Okay, the clear span means inner to inner face of the column. These two. Now there is one more thing: this center to center distance of the support. That means center of the column on the both sides, that is the center to center distance of the support. Now from these three informations we will be able to find the width of the support. That is also not known to us, but in your problem, say it will be given. In real problem, you will be able to assume it. So what is given as per condition? One is that clear span plus effective depth of the beam or the slab, center to center distance of the supports. No problem is coming. Whatever two guidelines are given related to some properties, those properties are also not known, because first one is clear span plus effective depth of the beam or slab. Effective depth or depth of the beam is not known, because we are given only the length, then center to center distance of the support. This may be known, this may not be known. If the width of the support, supporting width of the beam is given, then this is known to us. Okay, so if this is known to us, then what to do? So this is the condition for simply supported beam. See, I mentioned the clause here, clause number 22 2A IS 46 2000. Okay, and similarly, if it's a continuous beam, so the continuous beam you have studied in your structure. So for that, several conditions are given. So normally, whatever consider here, continuous beam means the end span, end span, intermediate span. Okay, the end spans are assumed. The end support is simply supported. End support is simply supported. Other supports are continuity. So if end support is contained, then how much? So what it is said? Okay, in case of continuous beam or slab, if the width of these supports are less than 1/12 of the clear span, the effective span shall be taken as 1.1 above. If the width of the supports are wider than, then the effective span shall be the following. See, it is linked. The width of the support, that means supporting width, not the supporting length, 1/12 of the span. Say the span is 5 meter. Span is 5 meter, 5,000. So 1/12 is 5,000 is 420 something. If it is in the first condition, that means clear span plus effective depth of the beam, if clear span plus effective depth of the slab, if it is slab, or center to center. But if the support more than that, or 600 this for end span, with one end fixed and other continuous, or for intermediate span, the effective span shall be clear span. Okay, so this thing we will not discuss at this moment. This paragraph we will not discuss at this moment. When we go for continuous beam, there we will discuss. Okay, and cantilever. Okay, then effective depth. Come the number 2. The effect. What is effective depth? Effective depth we have defined already. Effective depth from extreme compression surface to centroid of the tensile steel. To centroid of the tensile steel. Okay, so that we have already defined same conditions here. Now, how we will fix the B and D, that means effective depth and width. How we will fix? So for that, these thumb rules are mentioned by the IS 456. The effective depth of a beam or slab is the depth from the extreme compression surface of the central the control of deflection is okay. The particle deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are greater than the value of the obtained below. Now, this is the prompt theory of structure. Whenever load comes on the beam, there will be bending moment at different location. There will be shear force at different location, and because of the load acting gravity downward, there will be deflection. There will be deflection at different points. For a simply supported beam, if the load is acting on that beam is uniformly distributed W, then maximum deflection will occur at midspan point, and that value is 5 times WL to the power 4 divided by 384 times EI. This is the maximum deflection. Okay, this maximum deflection will occur. Now, that is the theory of structure. Now come to the design of structure. We'll get the value of deflection taking care of this expression. Now question is coming whether we will allow the structure to be deflected to that value. Definitely we will not allow. That is a maximum deflection. If deflection, now see here, if W increases, our deflection will increase. So example, deflection is going on increase, but after some, because of deflection, what is happening? The tension at bottom surface is going on increasing. Tension at bottom surface is going on increasing. So ultimately, a situation may arise. The tension is resisted by the tensile steel. So the stress that is induced because of the deflection on the tensile steel within the limiting value. Within the limiting value, if it goes beyond the limiting value, then the structure will fail. So for that, we have to give some limitation for deflection. Okay, so without going to theory of structure, IS 456 are giving some thumb rule by which whatever we use will be remain within the limiting value. Okay, what is said? The span to effective ratio, span to effective ratio, yeah, up to span 10 meter. If the span 10 meter, beyond the 10 meter, something different. 7 for cantilever, the 7 for simply supported, 20 for continuous, 26. Okay, that means span divided by small d should not be greater than 20. What is it? Provided the span ratio are not greater than this 20. So if it is 20, let us take the extreme value. L by small d is equal to 20. So d is equal to L by 20. So we will get one approximate value of effective depth required. Now here you add the effective cover. Effective cover means clear cover plus diameter of the stirrup plus half the diameter. So from this we will be able to get approximate depth of the panel. Okay. Now we require width. So for width, that I will tell slightly. So there is no. Now, when we start our problem, we should try a value less than. That means L by D, say approximately 15, approximately 16, or our. Okay. Now, if the span is more than 10, then what is happening? For the span of 10 meter, the values may be multiplied by 10 by span in meter, except for cantilever, in which deflection calculation should be made. Okay. Now, depending on the area and stress of the steel, the tension reinforcement, the values in A or B shall be modified by multiplying with the modification factor, depending on the. Okay. Now, since it is arbitrary or assumed, we should try to find out the actual value. So that actual value will be able to find out. So you see, we assumed L by D is equal to less than 20 for a simply supported beam. Less than 20. Say it is 50. 650. That means L by D is 50. Okay. Now whether this satisfies or not, that we will have to see. So for doing that, see, when we have taken L by small d is equal to 16, 15, 18, 20, whatever less than 20. Here, one thing we had not considered. We had assumed it is a solid beam. It is a solid beam. It is a solid beam without considering the material. Whether it is steel, whether it is pure concrete, whether it is concrete with steel, whether it is pre-stressed concrete, it is not considered. Now we are come to the consideration of the material. Our material is RCC. So the stress whatever induced in concrete, steel, if it is in steel in tension zone, if it is single reinforced member, and stress induced in steel in tension as well as compression, if it is a doubly reinforced member, the contribution of these two has to be considered. Otherwise, it will be a wrong design, it will be uneconomic. So how we will utilize these things? So for this, the code is given these conditions. Depending on area of steel for compression reinforcement, the values in C be modified by factor K obtained from figure 5. So this is the figure 5. This is the figure 5. This is available in your IS 46. I just reprinted from that. I just reprinted that. So see here, the bottom is percentage of tension steel. This is the modification factor. Okay. So whatever amount of steel we had utilized from bending moment point of view, that is known to us, that we had obtained in our solution of the circular reinforcement problem. After finding the amount of steel required, we had utilized the steel. Say after from the factored moment, and for a particular section, say our amount of steel required is 920 millimeter square. So if it is 920 millimeter, we are going to provide 5 numbers of 20. That means we are providing 1000 millimeter square divided by the effective area multiplied by 100, and percentage of steel. Percentage of steel. Percentage of steel. Okay. So here it is percentage of steel. Okay. Now from the percentage of steel, now see here Fs. The value of Fs. This is an expression. 0.58. Fs is equal to 0.58 multiplied by Fy into area of reinforcement steel required divided by area of reinforcement steel provided. 0.58 multiplied by Fy into area of steel required divided by area of steel provided. Everything is known to us. So from this, we will be able to find out the value of Fs. That means stress induced there. Now, from here, say our percentage of steel is say 0.4, 0.8, let's say this is 0.6. And Fs happens to be 150. Fs wants to be 150. So now we require modification factor. So this 0.5, you go vertically. Now here there are 5 curves for Fs. One is 120 for 120, is 145, one is 190, one is 240, and one is 280. So our value is 145. That means it is in between 145 and 150. Now how we will proceed? So see this curve, you proceed, you approximately locate. Say here it is 145 and 150. Okay, so from 0.5 vertically upward, so it is somewhere here. This is 145, this is 190, this is somewhere here. This is from your visual observation. You are to locate the approximate location of Fs. Now go horizontally. Now see it. So this value will be approximately 1 point, which is 1.2, 1.4, 1.6. It is approximately 1.5 or somewhere. So this is the modification factor. This is the modification factor. Where we will utilize this? So this we will utilize, whether I have written it or not, I don't know. No, I have not written it. So taking help of this, what we'll do, we'll try to find out the permissible span to depth ratio. So permissible span to depth ratio is equal to basic span to depth ratio multiplied by K1 multiplied by K2. Okay, so basic span to depth ratio, this is the basic span to depth ratio. That means span by D is equal to 20. This is the basic. Multiplied by K1. K1. So we'll get one value. So up to that value we can go. But we had utilized some value. Now whatever we had utilized, that value should be less than whatever value we had got after utilizing modification factor. By this way, we are able to fix the depth. Now width. Regarding width, no hard and fast rule. Regarding width, no hard and fast rule. In our normal construction, the width of beam may range from say 200 to at the best 350 width. And for that, there is one some rule that preferably it should be within within half to two-third of effective depth. Half to two-third of effective depth. If effective depth is 400, if effective depth is 400, then with 200 to two-third. Two-third means 80. 80 means 270. 290. That means from 200 to 290. Within this, it will vary. Okay, we will take comfortable value. We'll take comfortable value. Are you getting bored? Are you getting bored, or you are not at all following anything? No response? No response? You are not at all following?
We are, sir.
No, when we go for solution of the problem, it will be easier. I think here I want to just give the informations, whatever informations you are to require to utilize in your as an academic student as well as your. Okay, so by this way, we had fixed the cross section required. Cross section required. Okay, next we know the utility of the structure. So since we know the utility of the structure, there are two types of load. Basically, there are two types of load. One is dead load and another is superimposed load. So now we can find out dead load. Dead load means for this beam, it is self-weight. Okay, self-weight. So since we know the cross section B and overall depth D, so we'll be able to find out the dead load. B multiplied by capital D multiplied by 25. 25 is the unit weight of reinforced concrete. So this will give load per meter. Then superimposed load. So superimposed load, magnitude of superimposed load depending on the different utility, the defined values are there. It is available in IS 875 for 2. Okay. Say for a residential house, normal residential house, for floor, our superimposed load is 2 kilonewton per meter square. Okay, so if we know the span interval, we can transfer it per meter. So intensity of load acting on the beam is known to us. So once we know the intensity of the load on the beam, we'll be able to find out, since it is a simply supported beam, we'll be able to find out the maximum bending moment, which will occur at the midspan W L square by 8, and shear force at the face of the column, which is W small w L effective by 2. Okay, now utilize the partial safety factor. We'll be able to find out the factor moment and factor shear. Okay, so now we want to go to the chapter single reinforced section. The factor moment is known, breadth is known, known. Now our problem is only to find out the area of steel. So that we had calculated. Now here the IS gives some specification. The restriction, we have to provide some minimum amount of steel if we do not require, if at all we do not require the steel, and we cannot go beyond the value of some amount. That means minimum steel required and maximum steel required. So these conditions come. Sometimes it may happen when you do the theoretical calculation, you will see that amount of steel requires some value comes. It is a mathematics. Since it is a mathematics, it will give some answer, just like in a computer software. You give some information, it will give the result. No problem is coming. The result will be correct if your given informations are correct. For some result he will give. Some result will give. The since here also we will get some result. Now whether this result is acceptable or not. For that, IS 456 gives some restrictions. So see here, the first one is reinforcement, tension reinforcement, minimum tension reinforcement. Minimum tension reinforcement. So this almost similar expression I had gave you when I had gone for shear. Slight difference here. You see AST divided by BD is equal to 0.85 by FY. That means AST minimum, AST minimum. AST minimum will be equal to 0.85 BD by FY. BD is known to us. That means sometimes because of some situation you are providing some cross section, but whatever moment arises, the steel required is very less. Steel required is very less. Now, if steel required is very less, then what will be? If we, as a say structural engineer, you will provide that. No. It is said that there should be some minimum amount of steel. Why? Why minimum amount of steel? The one condition was that at least one reinforcement, one diameter should be available at each corner. Since if our beam is rectangular, then at 4 corners there's reinforcement. Now it is simply supported, so it is sagging, tension is going to occur at. So this is one condition. This is one condition from, that means from construction point of view. From construction point of view. Then our condition came deflection. At bottom there is tension. At bottom there is tension. Now whatever tension is going to induce because of the deflection, that may go beyond the shape value of the concrete. Beyond the shape value of the concrete. So if then there will be crack and finally it will collapse. Okay, so therefore to resist whatever probable tension by the steel, we have to provide some amount of steel. So that when we solve the problem, you'll be able to see. This is the first condition. That means there should be minimum amount of steel. AST is equal to AST minimum is equal to 0.85 BD divided by FY. Then there should be some maximum also. There should be some maximum also. You cannot utilize as many amount as steel required. Why? If the value is 0.04 B capital D. I have mentioned the clause. Maximum amount of steel that we can provide is 0.04, that means 4%. 4% of the cross section. That means amount of steel provided to be provided on a beam cannot be more than 4% cross section of the 4% of the gross cross section. It should be less. Why? Why? So one cause the number of diameter may be too much high, which may not be possible to accommodate on the width. I mean, a situation may arise that all the rods come in touch. That means no concrete will be able to get between two bars. But we may have to provide a different layers. So if different layers, then our effective depth will decrease. If effective depth decrease, then amount of steel required again it will increase. In short, we can say there will be congestion of reinforcement on the tension zone. There will be congestion of reinforcement in tension zone if we provide the amount of steel whatever it required with respect to factor of moment. So if steel required happens to be more than 4% of the gross section, then we have to redesign the section. That means we have to enlarge the section. Okay. So we are talking this single reinforced. We are talking with respect to single reinforced section. So compression reinforcement. Now, whatever statement is given, this is not with respect to single reinforced section. It is with respect to double reinforced section. So what is said here? What is said? If the maximum compression reinforcement shall not be more than 0.04 BD. BD. Now, if we go for double reinforced beam, a situation may arise. We are providing reinforcement in tension zone, no doubt. We have to provide reinforcement in compression zone also. The amount of reinforcement in compression zone also may be more than this, but in that case, we have to restrict here. Okay, that means in no case, whether it is in tension reinforcement or maximum amount of steel cannot be more than 4% of the gross section. Okay, very simple. Now come. We are providing reinforcement if it is single reinforced beam at the bottom layer. If it is single reinforced, simply supported. If it is single reinforced cantilever, we will have to provide reinforcement at upper surface. If it is double reinforced, then we have to provide both at bottom as well as top. Now here nothing is said about the side face. Now see, we are providing reinforcement both at lower level as well as upper level. These are binded by the stirrups. Now basic requirement for concrete, the reinforcement is to keep the concrete in its position. Now if depth of beam goes beyond some value, there is a probability of laterally bulging out of the concrete. Whatever stirrups are provided, these stirrups may not be able to prevent the lateral bulging out of the concrete. So under this situation, what our specifies that some reinforcements should be utilized on vertical face along the lengthwise direction of the beam on both the face, which is designated as lateral face reinforcement. But it has no any expression, only some percentage, probably 0.1% of the side face reinforcement. You see here, when the depth of wave exceeds 750 millimeter, side face reinforcement shall be provided along two faces. The total area of such reinforcement shall not be less than 0.1% of wave area. 0.1% of the wave area. So wave area means this word wave or wave was utilized, assuming that the beam is T beam. The beam is T beam. For a T section, there is one part wave, there is one part flange. But we are talking with respect to rectangular beams. So for rectangular beams, wave means total. So we know this total area B into effective depth out of this 0.1%. So very nominal. 0.1%, you find out the 0.1%. Area of steel required as a lateral steel on the two face divided by 2. That value you have to provide using some diameter, along the longitudinal direction on onto vertical faces. Okay. See, what these are not to remember. These are available in your code. These are available in your code. Now this cover, probably I have told you. This cover, this is again it is given in code. There should be cover, nominal cover or clear cover or effective cover. Nominal cover is from extreme compression or extreme concrete surface to outer face of the reinforcements. Outer face of the reinforcement. Okay. So for a reinforcement, we are providing main reinforcement, and together there we are providing the stirrup. That means from extreme concrete surface to bottom of the stirrup, that is the nominal cover or clear cover. Nominal cover or clear cover. But yeah, in our calculation, we will utilize the effective cover. Effective cover, yes. At the beginning, when we had started single input, we had obtained one this effective depth. We had already utilized effective depth. So effective depth is from extreme compression surface to centroid of the tensile steel. So we know that is D, small d. We have capital D, overall depth. So small d minus, capital D minus small d is equal to, we will get some value. So that will be effective cover. Effective depth plus effective cover is equal to overall depth. Okay. So here I probably mentioned some why we require. One is to protect the reinforcement against corrosion, to protect from fire, to develop sufficient bond strength, and this. Okay, now effective cover. This value I just repeated from the code. I just repeated. It is not my thing. It is not my thing. So this effective cover depends on the local condition. This value may not be same at all location, at all conditions. It varies from location to location, condition to condition. So if there are 5 conditions are given: mild exposure, moderate exposure, severe exposure, very severe exposure, extreme exposure. Say in our normal locations, if you are a student from say Kohima, it's a normal location. If you are a student from Imphal, it's a normal location. If you are a student from Aizal, it's a normal location. If you are student of Guwahati, normal location. But if you are a student of Bomdila, it's only because in Bomdila there is always ice. So it is not normal. It is extreme. Actually, it is extreme conditions. So that we have to specify under what condition we are going to design it. So with respect to that, these values are given. Okay, this is available in the code. Okay. So these are the basic things we require when we will go for design a beam. Should we continue? Should we continue?
No, sir.
No. You got fed up. Okay, in next class we'll try to see how to solve the problem.